In this set of lectures, I'd like to talk about how to communicate the story of a chemical reaction. We do this through formatting chemical formulas, which represent molecules, into chemical reactions. And as chemists, we like to take a lot of information and distill it down and abbreviate it so it looks like a small amount of information. And then when we read it later, we kind of unpack it to try to understand what's being communicated. So I'm going to talk through that process of taking information and abbreviating it into a chemical reaction, and then reading a chemical reaction and unpacking it to understand the story of the reaction. So I have a sentence that describes a chemical reaction, that hydrogen gas combusts in the presence of oxygen gas to form water as a gas. And so this sentence tells us what is happening when we combust hydrogen gas. And I can interpret that into a chemical formula. So I am told about hydrogen, oxygen, and water. And I'm going to discover from the context of the sentence which one of these are reactants and which ones are products. So our hydrogen is right here, and we can take hydrogen gas and we can abbreviate H2. An oxygen gas would be O2. These are both elements, and in their element state, they're actually covalently bonded diatomic molecules, which just means they're not a single atom alone, like you would have for a potassium element. And then these two combust and form water. So I'm writing water, H2O, as its chemical formula instead of writing out the word water. But another phrase that's important here for the context of this is the to form. And so the water in the sentence is being formed from the hydrogen and oxygen. That makes my water the product. Because the hydrogen and the oxygen are doing the action, they become the reactants. We will distinguish these in the chemical reaction with an arrow, and that arrow kind of means like before and after, or reactants and products. Here's our arrow right here, separating the two. So we don't use an equal sign like we might use in algebra. Instead, chemists use an arrow, and I think that better communicates the fact that something is happening rather than two sides of an equation are equal to each other. Because the two sides of this chemical equation might have the same number of atoms, but they might not be equal in their potential energy. And so we use the arrow to signify transformation. So we always format our chemical reactions so the reactants are on the left-hand side. And we make sure our products are always on the right side of the arrow. Another thing that you'll notice here is that I have these parentheses with these symbols. And these are, let's get a different color. So I have they're all G in this case. And these are coming from the sentence telling us the phase of here we go. The phase of our compounds. So we're told that water is in its gas state. So it's going to be like a vapor in the air. Same with oxygen and with hydrogen. We would change the G to an S if it was solid, or an L if it was a liquid. And these will help us understand how the reaction is taking place physically. So it's some physical information about what's happening. And in this case, our combustion reaction is really a bunch of gas igniting and forming water. A lot of times things will be dissolved in water and forming a solution, like we've talked about before. And those solutions will mix, and that's how a reaction will take place. Sometimes we'll take out solid and we'll grind it up into a powder and we'll mix it or heat it or something like that to bring two solids together to form a reaction. There's a lot of different ways they can take place. And so we want to represent that by including the phases of each of the molecules along with its chemical formula. And so the phase will always follow the chemical formula that it is giving us information about. Here's a list of the different symbols that we use when we're working with chemical equations. And we've covered a few of these already, right? So our arrows are always going to separate our reactants and our products. And then we'll have our different states of or phases or states of matter that we can use. And so we have solid, liquid, and gas. We also have this one that's interesting, aqueous, and it's AQ. So many reactions take place in water as a solution in water, where the water isn't really participating. It's just bringing some molecules together. And so we have a phase that we can describe it as AQ, aqueous, meaning dissolved in water. So some of these other ones, we've covered the arrows already. These ones are conditions that might be required of a reaction. We have a triangle. This means heat, like we had to apply heat or an ignition source. So with combustion, usually it requires like a flame to ignite it. So we might have written this with a little triangle. Oftentimes the heat symbol is written above or below the reaction arrow, and that's typically where you see it. We also have this other one below it, and it's representing light. And this is really showing frequency and Planck's constant, which equals the wavelength of light. And that's some really interesting chemistry to talk about that's a little bit outside the scope of this class, but we use this equation to represent, or part of the equation to represent light in our chemical equation. So I would probably write that over a arrow similar to the triangle to mean heat. If I was trying to say, well, this reaction will happen if it's exposed to a lot of sunlight. So I'd write it like that. Let's walk through another example. We'll have our symbols here. So here is a chemical equation, and let's work on interpreting it together. So I see we have Fe, that's iron, 2O3. O represents oxygen. And this is a solid, plus aluminum, solid. And so my phases are telling me in parentheses, the S tells me I'm in the solid phase. And then I see my arrow. So the two compounds that have been listed already are my reactants, and the ones that follow the arrow are going to be my products. And my products are an Fe on its own, so that's iron, and aluminum and oxygen as one of the second products. So I'm noticing right away that our aluminum and our iron are both elements. Something will be an element when it is just one chemical symbol by itself. And it might, like our oxygen, hydrogen, have a subscript, meaning there's more than one atom covalently bonded together. But if they're the same type of element, then it's in its element state. Now, the other two I'm noticing are ionic compounds. I have, in both cases, metal and non-metal bonded together. And so this will be an ionic compound or a salt, metal salt, as well. So I can now write this out into an equation. So I would interpret this as, and honestly, the ionic compound information isn't that important about the chemical reaction itself. It just helps me with naming it. So I would look at that iron bonded to the oxygen and be like, oh, that's iron oxide. And that's iron 3 oxide because I know my iron's going to have a +3 charge. I'm essentially doing the reverse crisscross rule, if that's familiar to you. My iron has a +3 charge, and my oxygen has a -2 charge. These form together and balance out to form 2 iron atoms and 3 oxygen atoms. Remember, our subscripts in our chemical formulas are telling us the number of atoms within our molecule. So we will have iron oxide. And it's going to react with our aluminum, but let's also let everyone know it's a solid rather than a gas or a liquid. So we could say solid iron oxide reacts with solid aluminum to form. So now I'm going to be communicating my products. And I have iron as one of my products that's in its element form. So I could form iron solid or solid iron. And my other one is similar to my iron oxide. This is aluminum oxide. And I don't need to put the charge in parentheses following the aluminum because it's not a transition metal. It just only forms a +3 ion based on its location in the periodic table. And so I can just leave it as aluminum oxide. Period. And that's a sentence that describes what's happening. We're bringing together iron oxide as a solid, probably like a powder, and aluminum as a powder, and mixing them together. And in this case, you do need some sort of ignition source. So we could put a little heat symbol if we wanted over our arrow to say, hey, you're going to have to ignite this. And then a reaction occurs and you'll have iron and aluminum oxide after it's done. And this is actually, if you've ever heard of the reaction, the thermite reaction, that's this one. It produces a ton of heat, a ton of light. It's so hot that it melts all these metals and you produce iron, molten iron that will then cool and form like a iron slag. And this one, you can actually kind of weld this way, which is interesting because it's such a hot reaction.